quite comfortable with some of the ideas of the quantum strings, and will become second nature because there will be lots of examples of things happening over and over. So I want to just remind you of what we were doing last time. Key thing is you had an operator L0 per, which was the sum over all integers. L0, in fact, I was just going to figure out that one. And the integers that alpha and p. Yes, all it's the first required. I'm sorry. Forgot that. They told me not to move this desk anymore. I almost broke it once, and then they say each time I move it, I disconnect everything. So that's it. No more moving. Okay. So this operator, as you remember, had a bit of a problem that the alpha minus n's are creation operators. These are annihilation operators if n is positive. But here was sum over all integers, so we had to reorder this. And that was difficult because it gives an infinity, and we called it the constant a. And therefore, this was equal to a well-ordered expression, which was the sum for all n greater or equal than 1 to infinity, alpha minus ni, alpha ni, plus a constant a that was infinite, but we argued that if we were allowed poetics license, we could set it equal to a nice number. That a came out to be equal to, was proportional to d minus 2. There was a minus 1/2 in front, or no, a plus 1/2 in front, and then was minus 1/12. So actually, it came out to be d minus 2 minus d minus 2 over 24. And I want you to focus on the fact that is going to be useful many times, is that this is the number of transverse dimensions. And it came from the commutator here when we had to sum over I. And therefore, for each dimension, each transverse dimension, we got a contribution to this constant, which is minus 124. So we call it the A contribution from a Neumann-Neumann direction. And why Neumann-Neumann direction? Because it was a free open string. So it had Neumann boundary conditions at the end. So we say that each coordinate gives you a minus 124. Anyway, we also introduced the Virasoro operators. And they had a nice property that the LNs, daggers, Hermitian conjugates were the L minus n. I didn't prove that last time. We wrote the formula for the LNs, and you can prove it. It's not difficult. You have to remember, of course, that alpha n I dagger was alpha minus ni. And then it's easy to prove this thing. Then there's the issue of what commutation relations these things satisfy. And that takes a bit of calculation. When you try to see what LM dagger, now perp, with LN perp is, we get m minus n. Lm plus n perp, and that you get if m plus n is different from 0. And the computation is relatively easy. You can take your Virasoro operators and do the commutator. Please read it or do it. It's something all of you, if you're new to string theory, should do. And this is when m plus n is different from 0, so this number is different from 0, these two don't add up to 0, then this is the result. But when m plus n add up to 0, there's an extra term, which is surprising, because it's not another Virasoro operator, but it's a number, and it's called a central charge, and it has the form 1 over 12 d minus 2 m cubed minus m delta m plus n comma 0. That central extension. Now, if in the homework that is due sometime later this week, there was a problem having to do with this, so maybe many of you are already familiar with what's going on. Having an algebra that has an extra number here, which people call central extension, and therefore they think of it as some operator anyway, and they put the unit operator sometimes here explicitly, so that you don't feel bad. You have operators, and suddenly a number. You really have an operator. It's 1 in there. This can cause problems with the Jacobi identity of a Lie algebra, but this type of central extension with m cubed and m is something you're going to show in the homework, or you've shown already, doesn't give you trouble. So that central extension is allowed. If you would put an m to the 5 here or an m to the 7th, somehow the algebra would not be consistent. It would just not work, would not satisfy the Jacobi identities. You wouldn't have an algebra. Moreover, this is a non-trivial central extension. That is, there's no way to redefine these operators in a simple way to get rid of this term. So it's something really very important and very, how would I say, very deep about the theory that gives you a central extension like that. This theory without the central extension, if you didn't have this term, this is called the Witt algebra, and it's a perfectly good Lie algebra. But this is still a good Lie algebra with a central extension. It's a very different one. So if you also have played with the redefinitions of these operators, it's possible to change the coefficient of the m term here, but not the m cubed term. So the m term is kind of trivial, but the m cubed is okay. So that's a Virasoro operator. Now, these Virasoro operators are going to be important for several reasons. First of all, and perhaps the most important one, is that they are needed for the construction of the Lorentz algebra. But another thing is that you wish to understand sometimes what they do. What do these operators do? So actually, they generate reparameterizations, special reparameterizations. So Virasoros generate reparameterizations. Of the world sheet. So they're funny operators, and how do they do that? That is a result of a calculation. It's a calculation that takes a few lines, and we're essentially going to just discuss the result. So you try to see what does the Virasoro operator do when commuted with a string coordinate, an open string coordinate. So this is a doable calculation. You remember there's a mode expansion for the x's, and therefore you know the LM in mode, so you can compute this. How you do it and how efficient you do it, it's another story. It can be done without getting into too much complication, or it can be a little long. But the result is the following. You get a function psi tau m times xi dot plus a function psi sigma m times xi prime. And what are these functions? These are calculable functions. They come out of the calculation, in other words. Psi tau m of tau and sigma is minus I e to the I m tau cosine m sigma, and psi sigma m of tau sigma is equal to e to the I m tau sine of m sigma. So so why do we say that this generates a reparameterization? It's a bit of language, but this is the idea in general. If you have an x coordinate of tau plus, and you want to change tau a little bit by psi tau m, and sigma, you want to change it by psi sigma m, then this is equal to xi of tau and sigma plus epsilon. And because of this variation, you get epsilon times psi tau times the dd tau of xi. So psi tau m xi dot plus psi sigma m xi prime, which is precisely what you get in the right-hand side of this. So we can basically say that this is xi of tau and sigma plus epsilon lm perp xi of tau and sigma. So it's an infinitesimal action of the Virasoro operators that changes the coordinates on the worldsheet. Now, these changes are a little unusual at first sight. There might be some disconcerting facts about this. But, for example, they also know what they're doing, these changes, because, for example, sigma, you know, you've parameterized from 0 to pi. And this can be thought as a change in sigma. So if you are at sigma equal pi, you get 0. So you don't push the range of sigma to go beyond 0 to pi. So that's because the Virasoro operators sort of know what's happening with the boundary conditions and everything of your theory. A little strange is that these parameters are complex. They shouldn't be, because tau and sigma are supposed to be real. So there's a simple resolution of that, and you probably remember from quantum mechanics is that only anti-Hermitian operators are the ones that generate the correct transformations on states or on operators. So that's why you have e to the IPX. This is a Hermitian operator with an I is an anti-Hermitian operator. E to the anti-Hermitian is unitary. Unitary operators are the ones that are good. So certainly this didn't produce a real diffeomorphism because the L's are not Hermitian. But you can form Hermitian combinations. So anti-Hermitian ops generate real transformations. And these combinations are, for example, Lm perp minus L minus M perp. If you do the dagger of this, it gives you this with a minus sign, it's anti-Hermitian, the other way around. Or you can form a Hermitian combination. Lm plus L minus M. That's Hermitian, but it's not Hermitian anymore with an I. So that's an anti-Hermitian operator, and those ones would generate real transformations. Now, I will not bother now to write them, but you could calculate them from there. You add the size of M minus the size of minus M in this case, or you add them and you multiply with an I, and you're supposed to get real things, and you will get real things. So that's about diffeomorphisms. There's another interesting thing about these Virasoro operators is that these reparameterizations they generate are very special. These are reparameterizations that actually preserve the constraints of our theory. So what were our constraints? So these reparameterizations preserve the constraints that we had that were d tau of x, the sigma of x equals 0, the relativistic product. This, you may remember, x dot x prime equals 0. And they preserve the x dot squared plus x prime squared equals 0. So they preserve these conditions. And these conditions, if you remember, when we impose very general class of gauges, like the Lightcon gauge or the static gauge, any of those gauges that had this n mu, x mu, we were led to these constraints. And these were the constraints that are satisfied by our gauge choices. Our gauge choices make this, the string coordinates satisfy this, and therefore the Virasoro operators that we've got now that generate reparameterizations are mindful of those conditions that we've put, and these things are still preserved. So I'm not doing that calculation again here, but it should give you an idea of mostly what's happening. So there's one operator that probably here you can relate to immediately. If we take the operator L0 perp, L0 perp, we generate a transformation for m equals 0, psi 0 tau. Psi 0 tau is minus I. This is 1, this is 1. And psi sigma 0 is 0. And that rings a bell, I think, because if you have L0 perp generates this thing, I L0 perp, which would be anti-Hermitian, would generate a constant translation in tau. Remember, psi tau changes tau. So I L0 perp generates something real, as it should be, because I L0 perp is anti-Hermitian, and it's a translation in the tau direction. And indeed, we've said that L0 perp is the Hamiltonian for an open string, so it should generate a time translation. So that's one Virasoro operator that is, has a simple interpretation. The most important one, L0 perp, is the one that is hard to order. It gives us the masses of the states because of this constant A, and it's also the Hamiltonian that generates time evolution. So I don't want to say much more about these Virasoro operators. Do you have any questions? Any questions about them? Yes. Why is it called the central charge? Yeah, it's called the central charge because this one, a central operator in mathematics is an operator that commutes with everything. So this one commutes with everything. So this term commutes with everything. So if you're doing a Jacobi identity and you have LM, and then suddenly you get this thing, this d minus 2, all this number times 1, and you have a commutator because you were doing a Jacobi identity. For example, LM, LK, LP. And suddenly these two things gave a number, and then what is the commutator of that number with LM is 0. So it's called central because it commutes with everybody. Now, that doesn't mean it's irrelevant because at the time you check the Jacobi identity, the central terms that appear at the first stage drop out, but then if you don't get a central term here, you get another LP or LK or something, and then the final commutator can give you a central extension.
Yes. You want to say that it's a Casimir operator?
Sorry?
It's a Casimir operator.
It's a very trivial Casimir operator, right? So Casimir operators are operators that commute with all the generators, like J squared in the theory of angular momentum. But it's not the central extension. You see, the algebra of angular momentum, Li Lj equal I epsilon I j k Lk. This is angular momentum algebra. Here, the Li squared is a Casimir, commutes with anything else. But try adding anything here. You will not succeed. In the best of cases, you will succeed to put something, and then you will show that it can be removed by a redefinition of the generator. There's no central extensions of this algebra. There are central extensions of the Virasoro algebra. It's very non-trivial. Some algebras that have central extensions. Yes, Ruben.
So does the fact that we can do those transformations without changing the gauge mean that our parameterization conditions of few chapters back didn't specify everything?
In some cases, our reparameterization conditions really let me say it this way. This is implied by our reparameterization conditions, but this doesn't imply our reparameterization conditions back. So our Lycon conditions cannot be derived from here, for example. So this is a weaker, if you say all your reparameterizations do is this, it's not true. The Lycon gauge condition is stronger than that, and it solved everything, and there was no reparameterizations really, in a sense, left that do that. But these reparameterizations, these general kind of reparameterizations are related to Virasoro conditions. Those, if you only impose this, then the Virasoro conditions leave it invalid.
Okay, so this does break some Lycon gauge conditions.
Yes, it will break some Lycon gauge conditions. So we'll now turn to the Okay, so Lorentz generators. Okay, you've calculated and you've discussed some of these Lorentz generators. It's M mu nu, which are given for the string by x. I'll put the indices down, mu nu, x mu, well, changes my x mu, p tau nu minus x nu, p tau mu, the sigma. These were our Lorentz generators. They were conserved charges associated to Lorentz symmetries. And we can write them explicitly, what they are. Well, we have the oscillator expansions for the coordinates, and we can write a formula. It will take this form, x0 p nu minus x0 nu p mu minus I, n equals 1 to infinity, 1 over n, alpha mu minus n, alpha n mu minus alpha nu minus n, alpha n mu. Okay, this formula, you know, like many of the formulas that I write, they all take like 5 minutes to derive. So we really can't do them here, but you have the oscillator expansion of the x's, the oscillator expansions of the p's, you multiply and you do it. Now this should be an inspiration for us to try to write the operator m minus I, that, as you remember, is the subtle operator of the Lycon. It is difficult to construct it, and it can cause trouble. So what would this be? Well, you try something like x0 minus pi just put those indices, minus x0I p minus I, sum from n equals 1 to infinity, 1 over n, alpha minus n minus alpha ni minus alpha minus ni, alpha n minus. And what are these? You probably remember some of that. I don't remember the coefficients exactly, but here they are. The alpha n's are the ln's. Alpha minus n's are the ln's. And we also have that p minus is supposed to be 1 over 2 alpha prime p plus L0 perp plus a, that constant that we don't know what it is. So the constant a that we filled around and did something a little illegal to fix is here in the p minus as well. And this operator is quite good, except that, again, it's not quite Hermitian. This one is Hermitian, but by the time you use the Lightcon, it's not, because this x0i and p minus do not commute, because p minus has L0 perp, and L0 perp is full of pi's. So x0i doesn't commute with it. So you have to do a little improvement here. So you have to do x0 minus pi. We saw that in the case of the particle. You put minus 1/2 x0i p minus plus p minus x0i. You make it Hermitian by hand. And if you want to write this in terms of Virasoro operator so that this looks nicer, to alpha prime 1 over p plus n equals 1 to infinity 1 over n L minus n dagger alpha ni minus alpha minus ni ln burp. Okay, that's the operator for you. So it involves a p minus. Every time you see a p minus, you should think of all this. So the constant a is there. The dimension of space-time is also here, because this I indices, or the sum over I indices in the Virasoro operators, depend on how many dimensions you have in space-time. So there's all the information of the theory is here, and you want to know if the Lorentz algebra holds. And the Lorentz algebra holding means that m minus I commutator with m minus j should be 0. With m minus j, is it equal to 0 or not? Now, we all complain sometimes that this is a long calculation, or this problem is a long calculation, this, that. Well, this is a long calculation. This is easily 15 pages or 20 pages of calculation. It's a nightmare of the calculation. In fact, when I was writing the book, I could not find any place where the calculation had really been done from the beginning to the end. Sort of crazy. There was an appendix that said, in a paper of Schwartz and Scherk, that said, oh, and we did part of this calculation, and after a lot of work we got this, and then in the next paper said, oh, using that result and another bad calculation, you get this, and that's the answer. So actually, however, this calculation, probably because I wrote in the book that actually nobody has written it from the beginning to the end, there's a couple of papers that appear in the archive already in the last few years doing it. It's a paper of 10 pages long, and the calculation goes from the beginning to the end. It's a tough calculation. There's no question about it. And the answer is it's a very important calculation because it actually determines everything that you care about. So what is it, the answer? The answer is m equal 1 to infinity alpha minus mi alpha m j minus alpha minus mj alpha mi. So there's a sum of, there's infinite terms that you get. So sum from m equal 1 to infinity of these things, and each one of them is multiplied by a number, and that number is m times 1 minus 124 b minus 2 plus 1 over m 124 b minus 2 plus a. Curved brackets like that. So look, it's an operator, an O operator that depends on m times the coefficient that depends on m, sum from m equal 1 to infinity. There's no hope of canceling different terms of the sum. Each OM is a different operator, completely different. You cannot, 01 plus 302 is not 0, or there's no linear combination that vanishes. So the only way this can be 0 is if this is 0. This is 0 for all n. Must be 0 for all n. And that, very quickly, you discover that if you have an m and a 1 over m, you say, I want it to be 0 for 1. And then you say, well, 1 times this number plus 1 times this number is 0. You want it to be 0 for 2. Then 2 times this number plus 1/2 of this number 0. Already with these two conditions, you discover that this must be 0 and this must be 0. There's no other way. So if those must be 0, from this one you obtain that 1 is equal to 1 over 24 d minus 2, and d is equal to 26. And from this equation, from the second equation, with d equal 26, you get 1 plus a is equal to 0, and a is equal to minus 1. So the important values about string theory come about from this calculation. Yes?
Is this A the same as we put?
Yes, it is the same a because we put it in here as p minus b existing.
So that your guy is minus 1 over 1 top.
No, no. If you, this is minus.
1 over top.
No, it's
that's
it's
a
stuck
minus
over
two,
there. Yeah, it's the same a. It's not the a of a single coordinate, but it's the same a. So a can be gotten without cheating by doing this calculation. But since nobody likes to do 15 pages calculation each time, everybody cheats and does that the sum from 1, 2, 3, 4, 5, 6, 7, 8, is minus 112. And with that, you get the right answer, and apparently in every possible case. So at this moment, we finally set for once and for all that this p minus is given by this, L0 per minus 1. And remember, the Hamiltonian was just essentially 2 alpha prime p minus p plus, and was L0 per when we first started. And I told you that remains to be correct, that the Hamiltonian is now this. So now that we have the Hamiltonian, we have the normal ordering constants, we can study the spectrum of the theory. Still, so remember the other thing we had, the mass squared was 1 over alpha prime, and you had the constant a that now we know is minus 1 plus the number operator, the perpendicular number operator, and that came from L0, and that perpendicular transverse number operator was the sum from k equal 1 to infinity of k, aki dagger, aki. So let's make sure you remember this. This came from L0. This is sort of the L0 minus 1 contribution. And here, this number operators for each oscillator, you have A dagger A. In the harmonic oscillator, the number operator is A dagger A. And this is A dagger A. And they have the algebra of creation and annihilation operators. That commutator is 1 between these two operators. Nevertheless, remember the kth oscillator has like weight k. So while the number operator has no thing in here, in the string, the various oscillators have more and more weight. So the k is here. So in particular, the number operator commuted with aki dagger is k, aki dagger. It's the fact that an ak contributes k units to the number operator. So, state space of the theory. Well, it's not too difficult. What did we have? x0i operators pi, x0 minus p plus, ANIs and NAI daggers. So we introduce a vacuum, a ground state of the string that is going to be labeled by the maximal set of commuting variables from these ones. You can choose a momenta and another momenta. And moreover, well, I won't repeat the fact that P plus acting on this operator, this is the eigenvalue of P plus, this is the eigenvalue of P transverse. P transverse is the collection of PIs. And moreover, killed by all A, N, I's. All the annihilation operators kill it. Remember, the ANs are annihilation operators. So this is like a ground state of all the harmonic oscillators of every single mode. There are infinitely many modes. For each spatial direction, there's infinitely many modes. A1, A2, A3 for direction 1, for direction 2, 3, 4, 5. All of them are killed by it. So, just to visualize your list of oscillators, you have A1 in the direction, the first direction is in direction 2. Remember, plus minus 2. A2, A1 in the direction 3, all up to A1 in the direction, say, 25. Dagger. These are all the creation oscillators with A1. Then you have A2 in the direction 2, and A2 in the direction 3, and then all this line, this 24 oscillators, then you have infinitely many of them. And they can all act in this state. So the typical state is written in this somewhat brief notation. It's okay, this notation. We write it like this. Product from n equals 1 to infinity. Product from I equals 2 to 25. So actually, it's basically a product over all the entries in here. Because you can have oscillators with n from 1 to infinity, the number, and you can have them in the direction from 2 to 25. So in order to specify a state, you have to see an, here is that oscillator, that creation operator. You have to say how many times it acts on the vacuum, on the ground state, I'm sorry. So you put a number here that we call lambda, so Ni. So this creation operator is raised to the power, this thing is an integer, belongs to the integers. that depends on n and I. So basically, you have to go through this whole infinite list and say, how many oscillators do I have of A12? You say 3, put 3. How many of this? How many of this? How many of this? How many of that? How many of everyone? And then you multiply them all and you let it act on the state. So lots of states. That notation, is it clear, this notation? You just multiply for every possible value of the labels, you can have a number of oscillators. Now, once you get to infinite dimensional spaces, things are very subtle. So actually, people put a constraint on this thing. They say, yes, this is the state, but only for a finite number of states, of oscillators, this is non-zero. So actually, the typical states, what people call the states in the Fock space, are things like that, but that they don't have an infinite number of oscillators acting on the back. These are Fock space tractable states. It eliminates actually many of the very most interesting states in the theory that are useful for other applications. Like, for example, you've studied in the harmonic oscillator things like minus alpha times a dagger on the vacuum, coherent states of the harmonic oscillator. This thing is an infinite series that has infinitely many things. That would not be acceptable in that definition of the Fock space states of the theory. These are additional kind of state dagger on the vacuum, and these are called squeeze states. People in optics love them. And there are all kinds of interesting states. So anyway, how much is this thing? I'm not moving it today, so we'll go here. The number operator associated to this state, how much is the eigenvalue of the number operator? Well, you say each A that is there contributes n units to the number operator. And we need to know how much it is because that will give you the mass of the state. And it appears lambda sub ni times. So I must sum over n and I, n times lambda ni. That's what it is. OK, time to discuss a few states. So let's begin. Well, n perp equals 0. These are the lowest lying states of the open string theory. Yes?
When you compute the number, why is the factor of n?
Because each of these ANs contributes n units to the number operator because of this relation. The number operator has a k in front. See the top equation.
So is it like an create an n particle?
No. It creates one particle of higher energy.
Yeah, but if the n is the particle number,
Is the what number?
if n is the number operator,
Yes.
n per, so the an just create one particle of the energy mode, which is n.
Right.
So if you count all the number of the particles, it should not be an n.
No, it is an n. This, first of all, it's fairly confusing to talk about particles yet. We're going to talk about particles in a second. This whole thing will represent a single particle. This is not many particles. Let's do this in a second, okay? N perp equals 0 means you cannot act with anything. So the only states that you got are the ground states. And for these ones, m squared is how much? Well, it's 1 over alpha prime minus 1 plus the value of n perp, which is 0. But let's just do it. You get minus 1 over alpha prime times the states. So these states have a crazy mass, m squared equal minus 1 over alpha prime, mass squared negative. And what are they? Well, we got accustomed to that. We knew them at the level of the point particle. These are one particle states of a scalar field. Remember, we identified these states at the level of the point particle with a scalar field. So these are scalar field of mass squared minus 1 over alpha prime. That's called the tachyon. Negative mass squared particles are called tachyons. These are not that exotic. The Higgs in the standard model begins as a tachyon because there's an instability, a negative mass squared, a positive lambda to the fourth, and the particle goes down and breaks the symmetry. So there is a particle like that here with a negative potential, and it's called the tachyon. And actually, that tachyon was a mystery in string theory for about 20, 30 years. And around 2010, Ashok Sen suggested what was the reason for the existence of this tachyon, and that eventually, in the next few years, it was understood how it all works out. So it's a very interesting story. I'll say a bit more about it later. But let's continue our catalog. N perp equals 1. Now that is more interesting. For n perp equals 1, you're going to get mass squared equals 0. That's massless state. So what states do we get? Well, to get n perp equals 1, I can act only with the A1 operator. I can act with I. It must be a dagger, and it acts on the ground states. I can only act with this one, and I can only act once, because otherwise I get too much n perp. N perp here gives you 1, and therefore these are the states that have 0 mass squared. And what are these states? There are d minus 2 of these, because the value I runs over d minus 2. And then there are massless states that are rotated. They're acted by Lorentz transformations on the index I. And I remind you of the states that we found in our Lighton quantization. We call them AP plus P transpose I dagger on the vacuum. In the field theory of the Maxwell field, we found this one photon states were states in which you act with one oscillator that has a label with a dagger, P plus this on the vacuum. These are isomorphic states. They have the same mass squared. They have the same labels. They have the same P plus and P transpose. They transform under Lorentz transformations the same way because it's the index I. So this is one photon states. The open string theory contains photons, contains somehow the massless field of a gauge field. So this is a fabulous result. This is the reason open string theory is interesting. This is a Maxwell field. States of the Maxwell field. One particle states of the Maxwell field. So gauge field or Maxwell field. Photon states. We can go one step higher. It's still interesting. And n perp equals 2. OK, how do we get n perp equals 2? Well, that's going to be m squared equal 1 over alpha prime. Over there. And now I have to get things with 2, number 2, acting on P plus P transfer. So I can act, OK, I can act with A1, I, dagger, all these labels, 3 labels per oscillator. That's a lot of labels. Now, that would have n perp equal 1. Maybe I can square it. Yeah, that would do it. But more generally, I can put another A1. And I'll call this one I and this one J. And that's it. Two things like that. That is a state with n perp equals 2. Are there more states with n perp equals 2?
No.
Yes or no? Yes? No? Sorry? A2, yes. There's the oscillator A2. Don't forget about it. A2I dagger. That has n perp equals 2. So 1 A2, P plus P transpose, that's it. These are all the states of this level. They have mass squared that much. And it's sort of fun to count how many states there are here. This runs over 24 values. And this, therefore, it's a, look, it's 24 values, but this is symmetric under I and J. So this counts a symmetric 24 by 24 matrix, which is 24 times 25 over 2 states. That gives you 300 states. And here are 24 states. A total of 324 states. But all of them are one particle states. The fact that you have 2 oscillators here doesn't mean that you have 2 particles. In quantum field theory, the oscillators carry the labels of P plus and P plus. So you have more oscillators, you have more particles. But in here, they are just all excitations of the ground state. There's just one label, P plus P transpose. So this is one heavy particle. Just like in a sense, this is just one particle. There's not many particles here. This is all one particle stuff. So remember, we talked about the first quantized action for particles. We gave one particle states, and then we do the field theory, and we do many particle states. If you want to get the many particles here nicely, you have to do string field theory. Yes?
So just to kind of get maybe some sort of intuition, if possible, typically use these I's, so the A and A daggers, oscillators, and think of them as particles at different points. How do we think about how we have these multiple oscillators in this case?
Well, you know, this multiple oscillators are just ways to construct more and more particles. So this is really computing for you the content of a single string. A single string can appear to be a photon, a tachyon, a Maxwell field, a fermion if it's a superstring. But a single string is one particle. So we are building the one particle states. Now, what is this, for example? People that do field theory, they introduce a field phi ij symmetric, and they call it something like a massive graviton, because it's a 2-index field, symmetric. And you say, no, but here is one index. But actually, this one index and this 2-index field combine into a larger field with gauge invariances, so that this part really is taken care. It's a whole artistry to construct the field theories of these states. But the important thing, you get 324 states, and people have a lot of fun counting how many states you get at different levels. At the next level, I won't write the states. You could, and you get 3,200 states. And the numbers go up and grow up, and it's very much fun. So I want to make 2 comments about the open string and then introduce one little thing about the closed string and finish there. Comments. First, the tachyon. So what is it about the tachyon? It shows some instability. Now, I told you that when you have an open string, floating in this room, if the open string is floating, is because there's a D brane filling this room. And that D brane has energy density. This was not understood until 2000 or 1999. Therefore, there is an energy density when you have your open strings floating around, because you have a D brane. And there is a tachyon with a potential. So where does this potential end? And the conjecture is that it ends at 0 energy. And this was verified using the string field theory to calculate it. And indeed, people found this potential looks like that. Ashok Sen was the one that made the conjecture. He came to MIT. We were calculating these things for a couple of years. And the potential came out to be like that. So actually, there's a ground state where the tachyon rolls down and sits down here. And what happens is very dramatic. Basically, your D brane disintegrates. Because here is the D brane, there's energy density, and here there's no D brane, there's no energy density anymore. So the D brane decays. The decay of a D brane is like an unstable object. In bosonic string, the D branes are unstable. So the D branes decay, and then the open strings, what do? They need D branes to exist. So the open strings, there's an open string, as the D brane decays, the open string ends, join, and become closed strings. And then they keep existing. At the end of the time, there's the tachyon has decayed, the D brane has decayed, and all that is left is closed strings. So that's why we're going to do closed strings right now. But these D branes are very interesting. Even in superstring theory, there are D branes, and they're used for inflation and for other things. It's really very interesting. The other comment I wanted to make is about oriented open strings. All our open strings are oriented. So you have an open string, you have a parameterization sigma from 0 to pi. It's oriented, 0 and pi. And you can ask about whether you can construct a theory with an orientation, playing with the orientation. And then you invent, as you will do in the homework, an operator that reverses the parameterization of a string. So the operator acting on an x mu of tau and sigma, and the operator acts from the left and from the right, will give you x of tau pi minus sigma, the string oriented in a reverse way. So you have an operator that changes the orientation of a string. Now, this is something that only exists quantum mechanically, in a sense. We can construct strings that are unoriented. What does it mean that they are unoriented? It doesn't mean that they don't have an orientation, but it means that they're invariant under reversal of orientation. But how can it be? If a string is oriented this way, it cannot be invariant under orientation reversal because it would go like that. But what you do is you produce a ket of a string oriented one way, and you add to it the state of a string oriented in the other way. And this can only be done in quantum mechanics. You cannot say that this string in classical physics is the superposition of this string in another. But in quantum mechanics, you can. So a string state can be a superposition of this string oriented this way plus oriented in the reverse way. So that when you try to reverse the orientation of this whole state, this becomes this and this is this. So the state is orientation invariant. So it's a miracle of the quantum theory that allows you to construct theories of unoriented strings that we will talk about. So to conclude, I want to say a couple of words about the closed string. Around 3-4 minutes. And leave it there. So when we do closed strings, we have to look at closed strings. we look at x mu of tau and sigma being equal to some function that moves to the left, as you know, plus some function that moves to the right. And there's nothing else that solves the wave equation. That has to be there. And we'll call for simplicity u equal tau plus sigma and v equal tau minus sigma, so that x mu of tau and sigma is equal to xl mu of u plus x right mu of v. The only thing I want to do now is just explore the periodicity condition. A closed string, we describe it by using a sigma that is identified with sigma plus 2 pi. Parameter runs from 0 to 2 pi, and that's it. So we want that x mu of tau sigma plus 2 pi be equal to x mu of tau and sigma. After you run through the closed string, you're back to the same point. This is perfectly okay if this x coordinate is a non-compact coordinate. If it would be a compact coordinate, something can change, but we'll leave it there for the moment. What does this tell you? Well, let's just look at this. What is x mu of tau plus sigma plus 2 pi? What happens to u when you do sigma plus 2 pi? U increases by 2 pi. So this x mu of tau sigma plus 2 pi is xl of u plus 2 pi plus x right of v, on the other hand, decreases by 2 pi, v minus 2 pi. And that should be equal to xl. I'm dropping the mu index, mu plus x right of v. Well, we can write this a little nicer by pulling the xl here, u plus 2 pi minus xlu. And on the other hand, you have here x right of v minus x right of v minus 2 pi. And this is the equation that really begins all the discussion of closed strings. It's the main equation. You should look at it and think about it because it says a lot of things. First of all, it says the following. Yes, the whole string is periodic, but no, the left wave and the right wave need not quite be periodic. In fact, the failure of the left wave to be periodic, this thing, is equal to the failure of the right wave to be periodic. So at the end of the day, the left and the right talk a little to each other, not too much. They're almost each periodic, but they're not. Now, another thing that you should think about. U and V are like tau and sigma. They're really independent variables, completely independent variables. They can be varied independently. You can vary U without varying V, increase this and increase that, or you can vary V without varying U. So they're really independent variables. When you say this function of U is equal to this function of V, you're really saying this better be a number and this better be a number. Because V and U can never be equal. So we'll discuss all that. But this, if you want to think about something before we continue, think about this equation and what it means. We'll also say that the derivatives of XL are periodic, and the derivatives of x right are periodic. So everything sort of comes from this one, and we'll develop that tomorrow. All right, we'll see you later.